Hello everybody, and welcome to our video on Lagrange multipliers. So the method of Lagrange multipliers is just basically going to give us an alternative approach to finding extreme values. So we saw in our previous section that some extreme value problems come with constraints, such as the region or domain that you're considering the problem on. So Lagrange multipliers are in particular helpful when there's a constraint involved in the equation, and sometimes these can actually save us quite a bit of work, though it may seem like a little bit of a strange technique at first. So, okay, what's this idea all about? Well, consider a function f of xy with a constraint of the form g of xy equals k. Then we see that maximizing f of xy is equivalent to finding the largest value of c such that the level curve f of xy equals c intersects with g of xy equals k. So what we're saying is this constraint tells us what x and y values are valid for the problem that we're trying to maximize, right? That's our orange curve. So if this curve just barely touches this point, f of xy in this case is 10, right? Then we see that 10 is the maximum value the function can take here, because if it wasn't, that would mean this curve must go a little bit further and there's a larger value of c that we can take. So what else does that tell us? Well, because these curves have to barely touch here, we're going to get that their tangent lines be the same. So this occurs when the curves barely touch, so they have a common tangent line. And if they have a common tangent line, then that means that their normal lines are going to be identical. So when you actually, when you look at the normal line here and for f, those are going to be identical, and therefore their gradient vectors are parallel, right? Because the normal line is going to be, just the direction, just a vector with direction, magnitude 1. And the gradient vector always goes in the direction of that normal line. Or I should say the normal vector, we can normalize that. So the normal line is the line passing through the normal vector. And the gradient vectors might have different sizes, but they're going to point in that same direction as the normal vector. So that just means that the gradient of f is equal to some multiple of the gradient of g at that point. So here we're using lambda as our multiple here, but this is just a constant multiple. So gradient of f equals a constant multiple of the gradient of g. So lambda in this context is called a Lagrange multiplier. And that brings us to the method of Lagrange multipliers. So to find the maximum and minimum values of f of xyz subject to the constraint g of xyz equals k. So here we're expressing this in terms of 3 variables. It also works in terms of 2. It's a little simpler to illustrate in terms of 2, but it's the same exact idea for 3 variables. So you've got a function, f of xyz, that you're seeking to minimize or maximize. And then you have some constraint. And we just need to assume that the extreme values exist and that the gradient of g is not equal to 0 on the surface g of xyz equals k. So our method starts with finding all values of x, y, z, and lambda such that the gradient of f equals lambda of times the gradient of g. Again, I'm getting my tongue all twisted up here. Let's try that again. The gradient of f equals lambda times the gradient of g. There we go. Where g of x, y, z is equal to k. So you still have to satisfy the constraint equation. So what we're going to do once we find those points, we're going to evaluate the function at all of those points, x, y, z, that result from step A. The largest of these values is the maximum value of f, and the smallest is the minimum value of f. So the thing I want to point out real quick is just that if we're setting the gradient of f equal to lambda times the gradient of g, well, the gradient of f is the partial derivatives in each component of this vector. And here, since this is lambda times the gradient of g, we'll get lambda times the partial derivative of g with respect to x, lambda times this partial derivative and lambda times this one. Okay, so if these two vectors are equal, then their coordinate components have to be equal as well. So the gradient of f equals lambda times the gradient of g implies the partial derivative of f with respect to x equals lambda times partial derivative of g with respect to x, and so forth and so on. So that's how we're going to approach solving these problems. And with that in mind, let's tackle a problem that we tackled before. So we solved this problem before using a more sort of, let's call it a standard technique. So a rectangular box without a lid is to be made from 12 meters squared of cardboard. Find the maximum volume of such a box. So here we've got V equals X times Y times Z. And our constraint is 12 equals the area of the sides of the box. And we've got the bottom side, let's call it the two left and right sides, and the two forward and back sides. And there's no top, there's no lid on this box. Okay, so what's the problem here? Well, the first problem is we can't directly apply the technique we want to use because, well, let me rephrase that. We can't do anything until we've taken the gradients, right? So for the previous technique, we had to solve for z, substitute into v, and then we had to take some partial derivatives, which were much more complex because of that substitution. In this case, first we just need to take some gradients. So that's actually a little bit easier here. So the gradient of v gives us yz, xz, and xy. So just the derivative with respect to x, then with respect to y, then with respect to z. And lambda times the gradient of g, just keep in mind g is always just the equation part. Here, the variable section, you know, we set our constant off to the side, and we're only worried about this for the function g of x, y, z. So this gives us lambda times the derivative with respect to x. So that's y plus 2z. And then lambda times the derivative with respect to y, so that's x plus 2z. And then the derivative with respect to z, which gives us 2x plus 2y. And times lambda, if I didn't say that. So now these two gradients should be equal, so we'll set each of their components equal. So we get yz equals lambda times y plus 2z. Xz equals lambda times x plus 2z. And xy equals lambda times 2x plus 2y. So this in general is actually pretty hard to solve algebraically. And that's the main difficulty of the Lagrange multiplier approach, is that you can get any sort of set of equations to solve, and there's no, straightforward, like, this is the approach you should take to solve all of these algebraically. You could end up with some very unique algebraic problems. And so a lot of times you just have to take a creative approach to solving them. And sometimes that's just going to be a little bit of puzzle solving, right? So in this case, what I notice here, I've got yz, xz, and xy. So all three of these equations, the left-hand side is really similar. So I notice that if I was to multiply this by x, this by y, and this by z, now all three of my equations are actually the same, are equal to one another. So I can just take my right-hand sides and set all of those equal. Lambda times y plus 2z equals lambda times x plus 2y. equals lambda times 2x plus 2y. So that means any two pairs of these need to be equal. So we can start solving the system by setting the first pair equal. And since we've got lambda in both of these, in fact, lambda's in all three, we can just cancel out that lambda, make this a little simpler. So this becomes y plus 2z equals x plus 2y. So I subtract y here and x here. Or, actually, I'll solve for z first. Let's solve for z first. So z equals, so I'll subtract the y. I get x plus y over 2. So x over 2 plus y over 2. Okay, now what else do I know? Oh, that should be x plus 2z here. Y plus 2z, x plus 2z. That was a typo. Oops. Well, let's just fix that up real quick. That messed up my my first step there. Okay, let's and I lost my x, y, z. Wow, that was multiple typos. So this should be times x, and this should be times y, and this should be times z. Okay. Let's try that again. I'll try to take that a little slower. So if I multiply these corresponding components out, I get xy plus 2xz equals xy plus 2yz equals 2xz plus 2yz. All right, that's a little bit better here. Now we'll take this first equation and set it equal. We get xy plus 2xz equals xy plus 2yz. And so these xy's cancel. And if I divide out the 2z, I get x equals y. Now I'll take my second pair of equations here. We've got xy plus 2yz equals 2xz plus 2yz. And I'll substitute y equals x into both of these, and I get x squared plus 2xz equals 2xz plus 2xz. So I can cancel those. Get x squared equals 2xz. Now, technically, I have to be concerned about a possible second answer for x, but the second answer for x would be negative, which doesn't make sense in the context of the problem. So I can just go ahead and not worry about that and divide by 2x here, which gives me x over 2 equals z. So now that gives me the ability to rewrite all of my variables in terms of x, and now I can plug this into my constraint equation, and I should be able to solve for x. So 12 equals x squared, because x times y is the same thing as x times x, plus 2x times z, but z is x over 2, so this is 2x squared over 2, plus 2x times x over 2, so again, this is 2x squared over 2. Those cancel, and I get 3x squared here. Divide out the 3, I get 4 equals x squared. Take the square root, and I get x equals 2. And that implies y equals 2, since they're equal. And that implies z equals 1. So v equal to 2 times 1, which is 4, is the maximum volume. Now, I wouldn't say that this approach was easy, but I'd say it was about half the level of computation when we approached this problem before. The challenge with the Lagrange multiplier method is you might end up with some algebra that is either really, really difficult to solve, or perhaps there's like a little clever trick you need to come up with that might be hard to think up the first time you see the problem. So don't always expect these problems to, be super easy, but it can potentially be half the work that using a more standard approach might take. So it's worth considering. Sometimes it can really save you a lot of time to use this approach. All right, let's go ahead and move on. So example 2 here, find the extreme values of the function f of xy equals x squared plus 2y squared on the circle, x squared plus y squared equals 1. Okay, so just keep in mind this means that g is the function x squared plus y squared. So we need our gradient of f, which is going to be 2x and 4y. So the derivative with respect to x and the derivative with respect to y. And then lambda times the gradient of g is going to be lambda 2x and lambda 2y. So if I set my components equal, I get 2x equals lambda 2x. And 4y equals lambda 2y. So there's a couple possibilities that could arise here. So the first possibility is lambda would have to be 1. So for 2x to be equal to lambda times 2x, you'd have lambda equals 1 or x equals 0. But let's think about the consequences of this. So if lambda equals 1, then that means that 4y equals 2y. So that would imply y equals 0. And if y equals 0, what does that tell us? So y equals 0 here. Lambda equals 1. So x could be anything at that point. So we'd have to check our constraint equation. So if y is 0, we get x squared equals 1. So that implies x is plus or minus 1. And if x is equal to 0, then y is going to be equal to plus or minus 1. Okay, so now let's consider this case 4y equals lambda times 2y. So then you get the possibility that lambda is 0. So, or not 0. Lambda is 2. Or y is 0. But if lambda is 2, then what does that tell us about x? So if lambda is 2, then we have 2x equals 4x. So that means x equals 0, but that covers this case here. So y is plus or minus 1. So we get the same thing there. And if y equals 0, then x equals plus or minus 1. So basically it boils down to the same cases. So we actually have 4 different possible points to consider. So f of 0, 1, which is 0 plus 2. So that's 2. F of 0, negative 1. And 0 still plus 2. So that's 2. F of 1, 0. Which is 1 plus 0. So that's 1. And f of negative 1, 0. Which is still 1 plus 0. So that's 1. So what does that tell us? That 1 is the absolute minimum. And 2 is the absolute maximum. All right, so that's it for example 2. I think that one's pretty reasonable. It's not a bad problem at all. Okay, so let's move on. Find the extreme values of the function f of xy equals x squared plus 2y squared on the disk. X squared plus y squared is less than or equal to 1. Okay, so now what do we have to keep in mind? Here, the restriction that we had put us strictly on the circle with radius 1. So just on the circle. Now we're looking at the disk, which includes everything in that circle. So since this constraint is not a strict equality, we have to treat the boundary, which is the x squared plus y squared equals 1 part, separate from what's inside. And dealing with the inside part, we have to go back to our critical point approach. So first we got to try to find a critical point of f. So the partial derivative with respect to x is 2x. And with respect to y is 4y. So if this first one is 0, that implies x is 0. And if the partial derivative with respect to y is 0, that implies y equals 0. And so our critical point is 0, 0. So 0, 0 is a critical point. And if we plug that into our function, we get 0. So in this context, this is the absolute minimum. And this boundary value of 2 is still the absolute maximum. All right, that's it for that example. So let's go ahead and move on. So now we're going to talk about problems that are a little more complicated. So these are Lagrange multiplier methods with 2 constraints. So let f of xyz be a function for which we wish to find extrema. Suppose that g of xyz equals k and h of xyz equals c are 2 constraints. So this means that we are looking for the extrema of f restricted to the curve C, which is the intersection of the 2 surfaces, g of xyz equals k and h of xyz equals c. So in other words, you've got 2 3-dimensional surfaces here, but when you intersect those surfaces, you're just going to get a set of points that forms a curve C. And from our previous discussion, we know that the gradient of f is orthogonal to the curve at that extreme point. We also know that the gradient of g will be orthogonal to its surface at that point, and the gradient of h will be orthogonal to its surface at that point. So both the gradients of g and h are orthogonal there. So what does that tell us? Well, that tells us that the gradient of f, that vector, is going to be in the same plane that's determined by these 2 vectors, g and h. So you've got like I'm not sure if I can even draw a decent picture of this offhand. So you've got 2 surfaces like this, and they intersect along some curve here. And when they intersect, they each have vectors that are orthogonal to that curve. So keep in mind, they're orthogonal to the curve, but there's 360 degrees around that curve that they could be at a right angle to. So they might both be orthogonal to the curve, but not be lined up perfectly with each other. But this gradient of f, that vector is going to be in the same plane with them. So like f might be here. The gradient of f. Point being that if the gradient of f is in the same vector as them, then you can represent it as a sum of constant multiples of those 2 other vectors. So a constant lambda times the gradient of g plus the constant mu times the gradient of h. So we're just saying you can combine these 2 vectors in some way. You might have to shrink one or stretch one out, whatever, to get to the same vector as f. So that's this relationship here. The gradient of f at the point equals lambda times the gradient of g at the point plus mu times the gradient of h at that point. So when we set this equations up, this results in a system of 5 equations. So 1 for each component of our vectors, and then the 2 constraints here. So the partial derivatives with respect to x of f equals lambda g times the derivative of g plus mu times the derivative of h, and likewise for the partial derivatives with respect to y and z. And then our two constraint equations still need to hold true. So you can see that this is a little bit more involved than the previous approach, but that kind of makes sense since the problem itself is more complex and involves multiple constraints in the equation. So let's take a look at an example problem here. Find the maximum value of the function f of x, y, z equals x plus 2y plus 3z on the curve of the intersection of the plane x minus y plus z equals 1 and the cylinder x squared plus y squared equals 1. So first, let's find our gradients. So nabla, the gradient of f equals, well, we've got the vector, partial derivative with respect to x, which is 1, and then with respect to y is 2, and with respect to z is 3. And we'll call this plane constraint the constraint for G, and we'll call this constraint the constraint for H. So we want lambda times the gradient of G, which gives us lambda times the derivative with respect to x, that's 1. Then lambda times the derivative with respect to y, which is -1. And then lambda times the derivative with respect to z, which is 1 again. So just to clean that up a little bit, that's lambda, negative lambda, lambda. And now we want mu times the gradient of h. The derivative with respect to x here is 2x, so that's mu times 2x. With respect to y is 2y, so that's mu times 2y. And with respect to z is just 0, because there is no z, so we get 0. So if I set up my equation, the gradient of f equals lambda times the gradient of g plus mu times the gradient of h, then that means that my components for f should be equal to the sum of the corresponding components for lambda g and mu h. So our system should look like this. 1 equals lambda plus mu times 2x. 2 equals negative lambda plus mu times 2y. And 3 equals lambda plus 0. So just lambda. Well, that's helpful because that gives us an immediate value for lambda, so that makes things a little bit easier. So if I take lambda and I plug it into my first equation here, I get 1 equals 3 plus 2 mu times x. And I could approach this a few different ways. I think I'm going to solve for mu equals first. So if I subtract 3, I get -2. And then I divide that by 2x, I get mu equals. So -2 divided by 2x is -1 over x. And I'm going to just write that mu a little cleaner. Okay, and now we've got 2 equals negative lambda plus mu times 2y. So 2 equals -3 plus mu times 2y. So here if I add 3, I get 1, and I divide by 2y, gives me mu equals 1 over 2y. Okay, well, I solved both of these for mu, but actually, what I really want to do is solve each one for x and y in terms of mu. So now that I'm thinking about it, I look at this constraint and go, if I had a formula for x and y here, I could plug them in and turn it into one variable. So let's try that. So that's easy enough. I multiply the x across and divide by mu, and I get x equals negative 1 over mu. And here I get y equals 1 over 2 mu. So now I can plug that result into my constraint equation. And what do I get? Well, we get negative 1 over mu squared plus 1 over 2 mu squared equals 1. This gives me 1 over mu squared plus 1 over 4 mu squared equals 1. So if I multiply this by 4 over 4, I get 5 over 4 mu squared equals 1. Multiply mu squared across, I get 5 over 4. And take the square root, that gives me mu equals plus or minus the square root of 5 over 2. Okay, so let me just think for a second, make sure I didn't make any minor mistakes here. Let's see. That seems good. It's always good to just double check your work a few times before you finalize anything. And I found a mistake. Good thing I checked. When I added 3 here, I should have gotten 5. So I should have had 5 over 2y equals mu. And that should have given me, for y, 5 over 2 mu. Okay, well, let's go ahead and fix that real quick. So this is 5. This is 5. Although that didn't change things too drastically. That gives us 9 over 4 mu squared. So I multiply the mu squared across, and then I take the square root, and I get mu equals plus or minus 3/2. No. I'm on a roll. I'm really on a roll. This is what happens when you record a bunch of these videos back to back to back. Okay, let's try that again. All the numbers start to look the same. 5 squared is 25, so that should be 29. I know how to square numbers now. All right, that's 29 over 4 mu squared equals 1. Multiply the mu squared across, and this time we get mu equals plus or minus the square root of 29 over 2. I like those other numbers better, though. They were nicer. Okay, now we're in business. So if I know this value for mu, that tells me what my values for x and y are. So let's go ahead and plug that in. Now, it's a little tricky here. We've got x equals negative 1 over plus or minus the square root of 29 over 2. So division is multiplication by the reciprocal. So this is negative 1 times plus or minus 2 over root 29. Now, it's important that we keep track of when our variables are going to be positive and negative, because that's dictated by which version of mu we're using. So when mu is the positive version, this x is going to be negative. So we actually need to flip this plus or minus symbol to minus plus. And now for y, we've got 5 over 2 times plus or minus the square root of 29 over 2. So the 2's here cancel. And this is just plus or minus 5 over root 29. So notice that when mu is positive, x is negative and y is positive. So just keep that in mind. You always get the x and y values in this case are going to have opposite signs. Okay, so now we can use our other constraint, x minus y plus z equals 1, to solve for z. So negative 2 over root 29 minus a positive 5 over root 29 plus z equals 1. So that's negative 7 over root 29. Add that across, I get z equals 1 plus 7 over root 29. And now if I plug in my other values for x and y, so I'll get a positive 2 over root 29 minus a negative 5 over root 29. So here this will be positive 7 over root 29, so I'll have to subtract that, and z will be equal to 1 minus 7 over root 29. So z is plus or minus, 1 plus or minus 7 over root 29. So now we just have to plug in these values into our function x plus 2y plus 3z. So if I start with my first values, I get negative 2 over root 29, 5 over root 29, and 1 plus 7 over root 29. What do we get? We get negative 2 over root 29 plus 2 times this, so that's plus 10 over root 29, plus 3 times this, so that's plus 3 plus 21 over root 29. So negative 2 plus 10, that's 8, plus 21, that's 29, so this becomes 3 plus root 29 over 29. Sorry, I flipped that around there. That should be 29 over root 29. But 29 divided by root 29 is just the radical of 29. So that's one value. And now if we evaluate this at our opposite values, so 2 over root 29, negative 5 over root 29, and 1 minus 7 over root 29. What do we get? We get 2 over root 29 plus 2 times this, which is negative 10 over root 29, plus 3 times this, so that's 3 minus 21 over root 29. And so this ends up being 3 minus 29 over radical 29, or 3 minus root 29. So that means this up here is our absolute maximum, and 3 minus root 29 is the absolute minimum. And that's it. We've made it through Lagrange multipliers, so thank you for sticking around and have a great day.